Good morning. Can you hear me and see the screen?
Sì, la sentiamo e vediamo.
Okay, so you can also read it. And here there are some statistics that I just checked on the e-learning platform, where we have, I found registered 138 students over 154 who are registered on the Microsoft Teams platform. So I prepared a number of quizzes for these two parts, and this will be also part of the questions that we posed in the first part of the exam. But it seems that it's not so interesting to try and to check your preparation with this quiz. So I will, if I don't see this number here increasing in the next few days, I think I will not propose you any exercise or quiz on the e-learning platform because it's useless. So it depends on you. If I receive here and if I see here a number of students which is increasing and will be at least, I don't say much, at least 20–30% of the total number of students, I will continue to propose something. Else it's useless. I don't waste time on this. I had also among the number of attempts probably that has been made on this exercise number 2, there'll be also someone who has not attempted yet to put a number inside, so I cannot track it. And I had a question from one student about this exercise. This exercise is the one where we have a two-stage vehicle where we can in practice calculate, we have all the data to easily calculate the delta V that can be achieved from the first, second stage and overall. It's just straightforward. We have masses, you can calculate the mass ratio and so having the specific parts delta V. The second part of the exercise asks to put 2 boosters and to see what happens. So the question was, can I do it analytically or I need iterations? And the answer is that I'm aware that actually, if I would like to see what happens adding these 2 boosters in terms of the payload and delta V that I can achieve, there will be some iterative process. But here, to avoid to you this iteration, I just asked you to verify that if we consider a new payload, which is increased of 1,780 kilograms, this new payload, we have to see if we are able to get the same delta V of the case without boosters. So because of this verification, you don't need to iterate. If I ask you what is the increase of payload that we can achieve with these 2 boosters, there was, for the same delta V, there was the need of make an iterative process. Of course, giving you already this, you don't need. I hope that this clarifies to the students who asked me about that, and to possibly to other interested students. So let's see something more. I left in the last practice class I just give you an exercise on solid rocket motor with quasi one-dimensional analysis. We had this problem. We have a converging section here and a propellant which is marked here. So here we have the solid propellant, and the black lines are walls, except where we have propellants. So we have a wall here, and here, and here. We consider 3 cross sections, 1, 2, and 3. We have data that should be already available to you from last class: gamma 1.2, R 320, joule kilogram Kelvin, dot M 150 kilogram per second, T0 3000 Kelvin. And also the exit area of this convergent nozzle. We know M1 equal to 0, M2 equal to 0.4, and M3 equal to 1. So it's a chocolate nozzle. And we have between 1 and 2, we have to consider mass addition with Ux equal to 0 and T0I equal to T0. 2, 3 will be isentropic flow. So what we have to compute here is the total pressure P01, P02, P03, and also A1, which is equal to A2, is also unknown, whereas we have the value of A3. So I don't know if you solved this problem. You have to divide it in 2 parts, 1, 2, and 2, 3, and in each of these parts we have we can apply a single driving potential, which is mass addition between 1 and 2, and area change between 2 and 3. So we can proceed knowing, as we know, the Mach number at different positions. So for instance, the fact that we know that the value of Mach number in 2 and 3 allow us to evaluate the ratio between areas 2 and 3, and so also the unknown area, which is the same between 1 and 2. Then we have to compute the total pressure, and based on the relations that we can obtain for isentropic flow and for the flow with mass addition, knowing the Mach numbers, we can relate this total pressure to each other. But we need an initial value. And to obtain this initial value, we should exploit the information that we have available. And so I have to compute this at a given point. We have this total pressure, which is the same in 2 and 3, isentropic flow means that also we can say immediately that P02 is equal to P03, T01 equal to T02, T03. We have no heat addition. And so we have to, with the mass flow rate and the Mach number and the total temperature, we have, let's say, something. We have 3 information, and 3 information a given section in cross section should allow us to get 2, if they are independent, to have our unknowns, which are 2 thermodynamic variables and 1 velocity or velocity related variable. So here what we can do, probably the easiest thing to do, is to refer to the Mach number 1 that we have here at Trot and say that our mass flow rate is, so we have directly the velocity related to this condition, because we can express here, we have Mach number 1, that means that we have that velocity is equal to the speed of sound, and we should consider here rho velocity is A and area. So we know this, and we can easily obtain this value. In fact, we have that A is square root gamma RT, and we know that T3 is equal to T03 over 1 plus delta M3 squared. This is 1, and so we have gamma, delta is 0.1, M3 is equal to 1, T03 is equal to 3000, so T3 is equal to 3000 over 1.1, which is 2727.3 Kelvin. And accordingly, A3, we have gamma and R, we have seen in the data, will be 1023.4 meters per second. So the fact that we know all the quantity in this expression here, except for the density, allow us to evaluate also this density, which is the second thermodynamic variable, is not m over a, and this will be equal to 4.886 kilogram per cubic meter. This is the density. No? The density is kilogram per cubic meter in the international system. Then for the pressure, thus we have value with large numbers in the international system. In Pascal, we often use kilopascal or megapascal or bar. And bar is convenient because 1 bar is close to the atmospheric pressure. So we have that P3 by the ideal gas equation of state will be rho RT, and it's 42.64 bar. So we know also the relation, the isentropic relation for the total pressure, 1 plus delta Mach number to gamma over gamma minus 1. This is always 1, is still 1. So we have that this P03 will be 75.54 bar. So we have got the total pressure P02. So what remains is still to evaluate A2, which is A1, and sorry, A3 by M3 over M2, 1 plus delta M2 squared, 1 plus delta M3 squared, two gamma plus 1 over 2 gamma minus 1. And so we obtain for this area, always recalling that M3 is equal to 1, we can obtain, this would be 0.000484 square meters. So that we have, if you like to see something without all these zeros, you can say that your diameter will be 2.48 centimeters at the inlet of the converging section, and D3, the throat diameter, will be 1.95 centimeters. So it remains the part related to the mass addition, where we have to evaluate the total pressure loss that we know occurs in this case, we have seen. And so we have to go back to the relations with y equal to 0. Y was you injected velocity over the local velocity, and if you are injecting in perpendicular direction, we have no contribution to momentum by this flow injection. So we have to consider the case with y equal to 0. And I recall that the relations were dm over m minus 1 plus gamma m squared, 1 plus delta m squared over m squared minus 1. And we also saw that this dp0 over p0 is minus gamma m squared d dot m over dot m. Comparing this, we can eliminate the mass addition and see the relation between the pressure loss and Mach number change in case of mass addition. So that we have that dp0 over p0 is gamma m squared minus 1 dm squared over twice 1 plus gamma m squared and 1 plus delta m squared. I think we have integrated this, or you can do with the usual in the usual way, if we didn't do in class, and this will allow us to write that P02 over P01 will be a relation governed by the initial and final Mach number. So we have 1 plus delta m2 squared over 1 plus delta m1 squared to gamma over gamma minus 1 that multiplies this term where we have 1 plus gamma m1 squared over 1 plus gamma m2 squared. So here we know that m2 is equal to 0.4 and m1 is equal to 0. Is one of the data, because we have no velocity, no injection at left hand side, so we can easily evaluate this ratio that will be equal to 0.92275, so that our P01 is equal to 81.86 bar. And so you see that we have a 6 bar pressure loss by mass addition that we have to take into account. You can note that we have the area, or sorry, the Mach number that we have at the exit of the of this part here, of where we have mass addition. So at the end of mass addition, we have Mach number here, which is governed by, in this problem, at this condition, let's say, is governed by the area ratio between 2 and 3. And so here, once we have this converging section, independently on how long is our region of mass addition, we always say the same. We always have the same pressure loss, that only depend on the fact that we have Mach number 0 at inlet and Mach number, in this case 0.4, or in general related to the area ratio between 2 and 3, only these quantities that govern the total pressure loss that we have in this, let's say, example of cylindrical mass addition. So just to out this, we have got a number of relations of between different quantities that we are using in these one-dimensional problems, and I would like to show you a summary of them that I'll make available always if you do something, and this will be or if you prefer, you always have this in the recording. That is your preferred way to follow this course. So I have it here. So you can see this this matrix of dependencies, where you have this phi that we see here. This phi is our 1 plus delta m squared, and so that appears in many relations. And here you have the relations related to only the area change, only the friction as the driving potential. This is only heat addition, and this will be at the end the case of mass addition with y equal to 0, which is the one that we were talking about in the last exercise. So for instance, in the case that we have only friction, we have no area change, and the same is true also in all these cases. So this is 1, 1, 1. Here, this is the ratio between the total temperature and the critical total temperature that we have in case of heat exchange. And this is the critical length that we have mentioned for the friction case, and its length will not appear in all other cases. And so on. We can continue with the relations related to the mass flow rate to critical mass flow rate, pressure to critical pressure, density to critical density, temperature to critical temperature, and velocity to critical velocity. And below you can also find the total pressure to critical total pressure, and you see here, for instance, is 1 because we have constant total pressure, and also the entropy to critical entropy. All these expressions are only function of the local Mach number and of the isentropic exponent gamma. And so, for instance, you see that what we saw in another case, it was yes, you see, for instance, here that we have the same relation that I mentioned. We saw this during class, that we have these relations are the same. Sì.
Potrebbe usare tipo un qualche puntatore quando indica sulle figure?
Io provo a scrivere perché il puntatore, questo non lo vedete?
Scrivendo, però un qualche riferimento visivo.
Questo adesso non vedete nulla? Non vedete un cursore che si muove?
No, il cursore no.
Ok, questa lavagna non mi permette di avere un puntatore. Va bene, diciamo, prendo nota. Adesso per oggi non ho soluzioni, dovrei cercare qualche soluzione. So this is why I'm putting some marker in this red here, these two red points indicate that we have the same relation. It was just for illustrating, and yes, I don't know how to do this at this moment. Okay, so you can take this as a reference that can be convenient to make different kind of calculations. Another one of that we like, what we have not done so far in terms of solution of one-dimensional flows is the case of heat addition. That, of course, is one of our interests. So let's do one exercise on this. And we have to determine the inlet and outlet condition in terms of P0, P, M, and T of gas flowing in a choked pipe. We have the mass flow rate is 100 kilograms per second. Specific heat ratio is 1.2. Molar mass is 20 kilogram per kilomole. Diameter is 10 centimeters. We know that, so we have to compute this in 1 and 2. And we have heat addition here. And but we know something. We know that the exit total temperature is equal to 2000 Kelvin. and in total temperature is 322 Kelvin. I think I give you all data. So we have to compute now temperature, Mach number. Well, let's say this is a choked flow, so we know that M2 is equal to 1. So with this data, we should evaluate our MTP and P0 in 1 and 2. I'll leave you a couple of minutes to think about this. Perhaps it's convenient I show you the table that I showed you before. If you have taken note of this data, so we are considering now this simple diabatic flow. And we have these relations that can be exploited for our computation.
Professore,
Sì.
può ripetere che cosa indica psi?
1 più 1 mezzi m quadro.
Grazie.
Prego. Can you see the arrow at this moment?
Sì.
So obviously the important relation here is this one, because we know the critical total temperature, which is the exit total temperature here. That means the total temperature in 2 is something that is known here. And we know also this T0, the total temperature in 1. So this ratio is actually T01 over T02 for us. And here we have just to put inside M1 instead of M. The problem that we have is that we cannot extract directly the Mach number from here. So we should make some attempt and try by linear interpolation to reach the final result. So I just copy this expression below. Specializing it for our case. And this is our psi that I wrote explicitly. So this should be equal to what we have, 322 over 2000. Or multiplied by 2000, this result I should have 322. So we can make we can select some tentative value, and we can obtain, for instance, if I try with M1 equal to 0.1, you obtain T01 equal to 86 Kelvin. So it's too low. It means that the correct Mach number is higher or lower than this one. If I have to select a new Mach number that to try to close this value, what shall I try? Something less than 0.1 or greater than 0.1?
Più grande?
Sì. Yes, it's greater than 0.1 because we are closer to the critical condition. 322 is closer to 2000 than 86. So we try, for instance, with 0.4, and we see what happens. You put this in this formula and you obtain 1000. So it should be something in between, and if we make further attempt, we can find. So it seems closer to 86 than to 1007. So I can try with 0.2, and I will obtain now exactly 322. So the result is this one. The correct one is this one. I have to learn how to do. So now you see that I'm pointing correctly the what I'm saying is that here the result is M1 equal to 0.2. So we have total temperature and Mach number, and at this point we can calculate everything, or more or less everything. Let's say that in 2, we have just to evaluate the critical values. That means that T2 is T02 over 1 plus delta. In this one, 818 Kelvin. As we have, yes, among data, probably I should give you, or you should recall, the universal gas constant. And as we have R and M, we can calculate also our gas constant. That will be R over M, and is equal to 415.7. So we can calculate speed of sound. And this is needed to exploit, as we did in the last exercise, the fact that it will be rho u, like A, by the area. And the area, of course, comes from the diameter. So this A is 952.4. The density is as a consequence of the above expression can be obtained by this relation, and will be 13.37 kilogram per cubic meters. And finally, also the required pressure. Okay, mass flow rate was given here. You see here the mass flow rate, and here the diameter that has been used to evaluate the area. So the exit section has been solved. We still have to evaluate quantities at the inlet, and I need another one of these relations. So I can, for instance, I can take this one and calculate pressure, and then the other quantities. So if I consider this one is gamma plus 1 plus gamma mu squared. This is P1 over P2 . And should be 212 bar. So that you see that we have large pressure change, and it could be interesting to see also the total pressure loss, and we can evaluate that at the inlet where the Mach number is 0.2, the total pressure is not so different. Will be 217 bar, and if you now evaluate pressure, total pressure in 2, we have pressure and Mach number also here. Here will be something more, of course, and is 179 bar. So we see here the pressure loss because of heat addition from 217 bar up to 179 bar. And we can also calculate then the other quantities and consider that this ratio can also be evaluated based on this relation here, of course, which is what we have done in steps. Very good. We stop here now up to 110 for a few minutes. And we will resume with further exercises.
Professore, scusi, posso fare una domanda?
Certo.
E sempre per quell'esercizio che le avevo chiesto sui learning, quindi diciamo non dobbiamo fare il metodo iterativo alla prima domanda, però invece quando chiede dopo calcolare il carico utile che è possibile portare allo stesso delta V usando 5 booster identici a quelli descritti sopra, in quel caso dobbiamo fare numericamente?
Sì, quella iterativa. C'era anche quella dei 5 booster, mi era sfuggito.
Ok, grazie.
Sì, era quella dei 5 booster, quindi che si riferiva?
Sì, cioè no, in verità la domanda era su entrambe per sapere se devo fare un procedimento diverso oppure no tra le due. Grazie.
Sì, grazie di averlo precisato.
Professore?
Sì.
Sì, volevo fare una domanda. Nel rapporto di pressioni P1 su P2 abbiamo usato il Mach di sezione d'ingresso?
Questo qui dice?
Esatto, sì.
Sì, Mach di sezione d'ingresso perché l'altro è 1. Quindi
Okay,
se ci mette Mach 2 in realtà troverebbe l'unità.
Ok, quindi dovrei ottenere 2.12 più o meno.
212 bar. Sono
Ok.
100 bar, sì, quindi 2.12 è il rapporto.
Ok, grazie mille.
Scusi, professore, posso fare una domanda?
Prego.
Ma Psi, quella che abbiamo visto nella tabella, è riferita al Mach 1? Cioè al Mach 1 d'ingresso?
E, diciamo, queste tabelle, no, sono tutte riferite alle condizioni critiche, per cui il numero non c'è, e il pedice non c'è un pedice sul numero di Mach, perché intendono che, scusate, intendono queste relazioni intendono che una delle due, in genere sono da due posizioni, sono tutte con M1 ed M2, però qui una delle due è quella critica, per cui sono sempre riferite ad M2 uguale a 1, quindi, o diciamo così, alla condizione critica. Per cui qui vedete un solo numero di Mach che può valere per tutte le sezioni nelle quali c'è quel flusso, per tutte le posizioni nelle quali c'è quel tipo di flusso, purché ci sia soltanto un driving potential in riferimento alla condizione critica. Nel nostro caso abbiamo che la sezione 2 è la sezione critica e quindi possiamo applicare questa relazione pensando alla posizione 1. Se avessimo avuto un Mach 0,8 nella sezione 2 anziché Mach 0,1, avrei potuto comunque utilizzare questa relazione facendo il rapporto tra T02 su T0 critico, T01 su T0 critico, ciascuno è scritto col suo numero di Mach, e faccio il rapporto tra le due. E quindi in quel caso apparivano sia M1 che M2. È la stessa cosa che facciamo con la nota legge delle aree, semplicemente lo facciamo per altri rapporti e per altre condizioni di flusso.
Ho capito, grazie mille.
Prego. So we pass now to exercises related to the ideal nozzle. And we start with the first exercise where we would like to calculate the exit Mach number ME of a nozzle showing thrust coefficient in adapted condition equal to 1.8. And we know that gases flowing within this nozzle are characterized by this gamma equal to 1.2. So the first thing that we like to compute is what is ME, and with this data, and then we would like to also to evaluate the value of DE, the exit diameter. We are considering our supersonic nozzle with exit condition here and throat condition here. So if we know that dt is equal to 5 centimeters, so this is the first part of our exercise. So we know the thrust coefficient in adapted conditions and gamma, and we like to evaluate our exit Mach number. So we have just to invert the expression for the thrust coefficient. So we know this relation, this expression that we have seen and we have analyzed during lecture, and we see that there is a direct relation among gamma, thrust coefficient, and the expansion ratio P0 over PE, which in turn is related to the exit velocity, to the exit Mach number. And in fact, we are assuming isentropic flow where we know that this relation, there will be this relation between the Mach number, total pressure, and exit pressure. So we can obtain, we can invert this relation. Okay, this relation here, we can do it together. So of course we need also the function of Van den Kerkhove that can be obtained by this relation. And by substitution here, I also can obtain the value of P over P0 to gamma minus 1 over gamma, which is the quantity that we need to calculate our ME. So then we can substitute here and obtain that ME is equal to square root 1 over delta P0 over PE. Minus 1 over gamma minus 1. And so we can replace it here. This would be 1 over 0.358. And as a consequence, we obtain that ME is equal to 4.234. So notice here that we are in this expression of thrust coefficient, we assume that we are considering choked flow. We call this that is one important assumption that we are considering, as well as the one that we used here, and which is the assumption of isentropic flow. So this was the first question. Then the second one is the diameter of the exit, and of course here we can use the area Mach number relation. And this is also dE over dt squared, so that we have epsilon, this area ratio, is equal to 39.71, and our dE will be equal to 0.315 meters. Okay, so this is a way of solving this exercise where it was required the exit diameter and the exit Mach number. Now let's continue with another part of the same exercise, so that because we can ask to evaluate at this point if this was the adapted thrust coefficient, we can evaluate now. We have all the information to evaluate also the vacuum thrust coefficient. So the thrust coefficient that we would obtain in conditions where the atmospheric pressure is negligible. So I would like to evaluate in the second part what will be the vacuum thrust coefficient, and then assuming the same value of ME, we would like to evaluate thrust coefficient in adapted condition, thrust coefficient in vacuum, and the exit diameter if we change gas with the gas having gamma 1.4. So we complete the evaluation that we have done for this first condition with gas with gamma 1.2, evaluating also the vacuum thrust coefficient, and then we change the gas and we see what happens if we assume the same exit Mach number. So in the first part, of course, this vacuum thrust coefficient is just, you recall, the adapted one plus epsilon PE over P0. Consider that from this data, we can also see that PE over P0 is equal to and the inverse P0 over P is 474.6. So you have the value I just highlighted in the red line are a result of obtained gamma 1.2. And this point is also direct computation, the one that we obtain assuming gamma 1.4, because we know the exit Mach number, which is an information that allows us to evaluate everything. If we know the Mach number, we have the pressure ratio, we have the area ratio, and so also the required solutions for DE, for the thrust coefficient, and for the vacuum thrust coefficient. So be careful. First of all, you should consider the right value of gamma. Of capital gamma. And then you use the same expression that you have shown before for the evaluation. So we have ME, of course, is our input. Epsilon will be, in this case, 13.18. To be compared with this one, and you see that it's quite smaller value of epsilon that is needed for gamma 1.4 gas to reach the same Mach number. And what would be the pressure ratio? So of course this means also that the diameter that was one of the requested output is 0.181. Of course it's quite less than what we had before. And it's also interesting to see what is the pressure ratio we achieve we have seen that actually we are trying to define our area ratio on the basis of the resulting pressure ratio, so that we can compare with the atmospheric value. And in this case we have also less pressure ratio. And we have also seen in class that thrust coefficient is improved when you have lower gamma. So here, having higher gamma with this gamma 1.4, we have that our adapted CF will be 1.6 and the vacuum CF will be 1.666. So you see the differences that we have with different gamma with the same exit Mach number. This is just with Mach number, it's just straightforward, and we can make also something, some different reasoning, but we need to iterate. And just to make some consideration, or if you would like to make your iterative procedure, we can compare, for instance, what happens with the same geometry, just changing the gas. So if we have same geometry, means the same AE over AT, the same epsilon. So if instead of considering same ME, we consider now same epsilon. So we have to find the Mach number such that we have with gamma 1.4 the same epsilon that we have got with Mach number 4.234 and gamma equal to 1.2. So we can make some attempt using different value of the Mach number, and we obtain the right area ratio with Mach 5.6. So always with gamma 1.4 and Mach 5.6, we have epsilon is equal to the requested value 39.71, and to this value it corresponds with higher Mach number, as I said, and then the higher pressure ratio that compared to this 474.6, it would be now 1035.8, and the corresponding, so this is a higher area ratio with respect to the former case that was 13, and it means that for the same gas we are closer to the maximum value of thrust coefficient. So we'll be here, we'll get adapted value of 1.682 that you see is higher than the vacuum value that we have got with the lower area ratio, and a vacuum value of 1.71. Consider that the maximum value that can be achieved with gamma 1.4, recall the maximum value is gamma square root to gamma minus 1, and will be for gamma 1.2 and gamma 1.4 respectively 2.246 or 1.812. So you see here we should compare this value that we have got in vacuum with the maximum value, and so it's 1.7 compared to 1.8. That means that we are more or less close to 90% of the maximum value of thrust coefficient. Another further comparison can be made now considering the same pressure ratio of the gamma 1.2 case, and for this it's again you have to, well, no, in this case it's not, you don't need iteration because you have this P0 FP, you can evaluate your Mach number. It will be 4.9. And we see that in this case we have something in between. So we have epsilon 23.21, which is greater than the first and lower than the second. And we have, of course, the given value of P0 FP. And as we have that this area ratio is between these two, this will be also the case for our thrust coefficient. .697. So this was an exercise just to start with relations concerning the thrust coefficient, and this is, let's say, the kind of exercise we should be able to handle easily. And so we can pass now to a second exercise, always related to area ratio, thrust coefficient, and adapted versus vacuum operation. But we introduce here also the characteristic velocity. So we consider now a nozzle of a gas characterized by a characteristic velocity of 1800 meters per second. We know that we have a total pressure of 50 bar and a throat diameter of 15 centimeters. We know that gamma is equal to 1.2 and that our nozzle is adapted at sea level. So with this information, we should evaluate thrust, specific impulse at sea level and in vacuum condition. And also the thrust coefficient. So you see here that we have the quantities needed to have dimensional values. Say we can evaluate the size of our engine in terms of thrust. So recall that it's an extensive variable that here can be determined because we know a pressure and a dimension, which is throat diameter. Whereas we, in the former exercise, we were considering only non-dimensional quantities. We had pressure ratios, we had Mach number, we had thrust coefficient. There was no, well, of course, we had diameter, so in principle something can be said, but not everything, because we didn't have a value of pressure, so we couldn't see the thrust level of the engine that we have in the former exercise. In this case, we have size, but we have also pressure, so we can go back to the thrust value, which is related through total pressure and throat area to the thrust coefficient, which is a non-dimensional quantity. So what we have to do here? So the important information is that the nozzle is adapted at sea level. So you see that the information that nozzle is adapted at sea level allow us to know what is the exit pressure. So let's assume that the atmospheric pressure is 1 bar, and in this way we know the important quantity, which is P0 over PE, to tell us about the area ratio, the exit Mach number, and the adapted thrust coefficient, and also the vacuum thrust coefficient. So to make this computation, again, we can evaluate our capital gamma, which is, again, of course, it's always the same for the same gamma, and so here we can consider 648. And our epsilon, we can calculate it from this relation. Is 2 over gamma, and 1 minus PE over P0, gamma minus 1 over gamma. So the result is 7.05 for epsilon. And then we can evaluate our CFCSL, sea level, that will be equal to adapted sea level, the adapted thrust coefficient from the relation that we are already using in the foreman exercise. So the same gamma as before, but we have a smaller pressure ratio. Is this time is 50 compared to 400 that we had in the other exercise, and so we have an area ratio which is 7 compared to how much it was compared to 39, and so we have a quite smaller value of the thrust coefficient. Then we can, at this point, because what we are doing here with this assumption is that 0FP is 50, and so we have also the evaluation of the vacuum thrust coefficient. So this is sea level because this is the adapted value, and it will be 1.69. And what we had to compute, at this point we have to compute thrust. So we need the throat area, we have the throat diameter, so we can compute and obtain this value, and it follows that F at sea level is equal to 137.4 kilonewtons. So this comes from this relation. So what will be the specific impulse? We recall what we have seen last time, that specific impulse is the product of characteristic velocity and thrust coefficient. We have among data the characteristic velocity, so we can evaluate through the thrust coefficient the specific impulse that we have at sea level. And it will be 2,798.7 meters per second. And the other thing that we have to evaluate is at vacuum. So we have F at vacuum will be CF vacuum at 0.8, so it will be 149.8, and you see that we have increased significantly the thrust from sea level to vacuum conditions, and the specific impulse will be also increased 3,052.4 meters per second, 211.5 seconds. we have seen the maximum thrust coefficient. We can see here we have seen before that this is 2.246 for gamma 1.2, and so we see that the maximum specific impulse that we can obtain in this case is 4034.8. So you see here that having expanded not so much our jet, because we have just this 7 as the area ratio and 50 as the expansion ratio, our specific impulse is rather small. Also in vacuum condition is 3000 compared to what theoretically we can reach with expanding up to zero pressure with an area ratio of infinity. That is of course theoretical, but is the upper boundary that here is rather far. And this is far because we have a limited, we are only exploiting a limited pressure ratio. Final exercise for today. We consider now a rocket operating in overexpanded condition at sea level. So say at sea level we have again PA is equal to 1 bar, and the nozzle is operating at the limit of overexpansion before separation. So it's operating with we know that the limit is coming from this value of pi, that is the ambient to exit pressure, that is assumed to be for this nozzle equal to 4. So with this information we are working at sea level. We would like to work at the limit of flow separation. So we don't like to have flow separation, but we will be as close as possible because we like to overexpand and adapt at higher altitudes. And we have also that C star characteristic velocity is yes, I have to check this value, but should be 2217 meters per second. Now, if we know that specific impulse is 430 seconds in adapted condition, and that molar mass is 14 kilogram per kilomole, we would like to know the values of total temperature and total pressure that we have in this nozzle. So we know the ambient pressure, the fact that we are operating at sea level at limiting condition for the separation. We have C star, we know the specific impulse and adapted condition, and we like to know which are the values of total temperature and total pressure. To do that, we assume that our gamma is 1.2, that G0 is 9.81 meters squared second, and R is 8314 joule kilogram Kelvin. we also know for the second part of the exercise, we would like to know what is the adaptation altitude assuming that pressure changes with altitude with a law, which is the following. Pressure is sea level pressure, 1 minus 0.0226 C 5.256. And this is very provided Z is less than 11 kilometers, and here this is in kilometers. Kilometers, not kilograms. Okay, so this is for the second part. The first part is this one. The second part is this one. So we have to evaluate these quantities. Here we have an important information that is, if we operate at sea level and PA is equal to 1 bar, with this pi equal to 4, it means that at sea level the exit pressure is 1/4, that is 0.25 bar. So we know the exit pressure, we know the specific impulse and the characteristic velocity. So from specific impulse and characteristic velocity we can get the thrust coefficient, and from thrust coefficient we can obtain from the thrust coefficient we can obtain the corresponding pressure ratio. Once you know the pressure ratio and you know the exit pressure, we can obtain the total pressure, whereas the total temperature is related to the characteristic velocity by the expression that you have got in class in case of our ideal nozzle. So we can obtain total pressure, we can obtain total temperature, and then you have just to find at which altitude you reach the pressure of 0.25 bar. So this is you can do this exercise, and if you it's also a simple exercise, but this kind of exercise is important to practice with thrust coefficient and characteristic velocity, specific impulse, expansion ratio. That is something that, as I mentioned before, we should handle with should easily handle. Okay, we can stop here for today.